Okay, everyone, let's find a seat so that we can start on time. Well, we're already 4 minutes late, but it's okay. So I think we can just let Francesca start. We start with this wonderful music and a wonderful lecture, I'm sure.
So thank you, John. It's really a pleasure to be with you. Thank you so much for the invitation. And yes, I start with some music because I think we need some inspiration for this part. So this guy is a musician from Italy who got inspired by Loop Quantum Gravity for his music. So we can be inspired by him for our journey into quantum gravity today. And I want to start so, of course, first of all, very nice to meet you. I'm Francesca Vidotto. I am a professor in Canada, soon to move to Spain. And I would like, first of all, to say a word. I have these images in my slides. They are taken from the cover of the book I wrote some years ago with Carlo Rovelli. And you can find the book online. So it's not an advertisement for the publisher. It's an advertisement so that you can go online, you can pick up the text, and you can use it as a guide through our lectures, okay? What are these lectures about? They are about covariant loop quantum gravity. So this morning, Christina did all the hard work, all the hard lifting to start to introduce some mathematical tools that later will be useful to discuss the canonical dynamics of loop quantum gravity. In these lectures, instead, we focus on the covariant dynamics. And it's all loop quantum gravity, of course. So that means that we all use the same quantization techniques. We all use the same kinematical Hilbert space, the same observables. Even though I wanted to discuss them with slightly different flavors, and that can be more appropriate to discuss the covariant dynamics. So I wanted to start with a little bit of history. And so this history starts a long time ago. And the goal was to try to make sense of this path integral here. So our goal in these lectures, it's the same. We have an answer today. So Meissner, back in the 50s, wrote this expression that was just an expression that meant that we wanted the path integral over geometries. So here we have the Einstein-Hilbert action that is a function of my metric, so a function of my geometries. We want to integrate, or better, to sum over geometries. And notice here that the integral is over my boundary of some four-dimensional geometries. So I have here a trimetric. So I wanted to make sense of this integral, and by the end of these lectures, you will see how we can extract a number from this formal expression. So I would say one of the main results of loop quantum gravity of the past 15 years is that, yes, we can do this computation. We can do it in 4 dimensions in the Lorentzian, fully Lorentzian space-time. And we can extract numbers, and we can compute physical stuff, black holes, cosmology, and so on. So, of course, this was a long journey to arrive to what we have today. One of the ingredients was to use Regge calculus. Unfortunately, the lectures on Regge calculus by Bianca Dietrich will be later in the week. So I will make some references to Regge calculus So wait for the lectures by Bianca later. So the only thing that I need you to remember about Reggio Calculus at this point is the fact that Reggio Calculus is a formalism that allows to truncate the degrees of freedom of general relativity that are infinite to a finite number of degrees of freedom. So as usual, when we do, for instance, quantum field theory, when we truncate the theory with a finite number of degrees of freedom, well, we can do computations. So for instance, when you compute things on a computer, this is also what you do. You do a discretization of your theory. So Reggio Calculus, in fact, was born, in a sense, in a context in which people wanted to start to do numerical computations for GR. Then nowadays, people don't use Reggio Calculus anymore. But that was the idea, discretize GR so that it becomes more manageable and more computable. And by the way, it may also become in an appropriate shape so that we can quantize it. So then, of course, next step is that at a certain point, Wheeler and DeWitt wrote basically the Schrödinger equation for general relativity. So the Wheeler-DeWitt equation is the analog of the Schrödinger equation for GR, except that, as you have seen, general relativity is a theory that is totally constrained. So you don't have a preferred time. So this was puzzling everybody, but it's not a problem. We just have to use relational quantities to describe the dynamics. And an ingredient that we are gonna use in what will come later from another giant, another grandfather of quantum gravity, that is Roger Penrose, is the spin geometry theorem. That is maybe the first attempt really to write a theory of quantum gravity just from a combinatorial perspective, a bottom-up, in a bottom-up way. So I will not say more than this because this will be exactly what we will discuss later. So by the end of this hour, you will know what the spin geometry theorem is about. And this is somehow the old quantum gravity, okay? So what about the more recent quantum gravity, where the journey in loop quantum gravity started? Well, as we have seen in the previous lectures, first of all, as I used to say, very often to solve a problem, it amounts to find the right variables in which you can work properly. So this is what happened with the work of Abai Ashtekar, that was working on the Hamiltonian formulation of general relativity and defined Ashtekar variables that are the first step towards having a quantization of gravity. And then, if you want, the putative day of birth of loop quantum gravity is when Lee Smolin and Carlo Rovelli found a solution of the Wheeler-DeWitt equation. So I told you before, somehow the Wheeler-DeWitt equation is a Schrödinger equation for the gravitational field. Big problem, nobody was understanding it, nobody knew how to solve this equation. And then after the work also by Ted Jacobson, Carlo and Lee were able to find a solution of this equation that was employing these loops, phantomatic loops. And this is the beginning of loop quantum gravity. A few years later, then if you wanted to compute things in gravity, and gravity is about space-time, it's about geometry, then of course you need to find a way to compute geometrical quantities. So what are geometrical quantities? Well, of course, it's about distances, but also area, volumes, angles. You can think about them from your Geometry 101 in kindergarten. So the problem is that you have to build this stuff in the quantum theory, okay? And this is what started from in the 90s. Again, by the end of this hour, you will know more about this, so don't worry. But then, and then in that period, there was the big development of the canonical dynamics. So you can think of your Hamiltonian as an object that you can build up from your geometrical operators, and then there is a big work going on to try to define properly this object. But then somehow parallelly, there was the beginning of this covariant dynamics. So instead of using the Hamiltonian to describe the evolution of our states of a quantum geometry, Carlo with Michael Reisenberg brought for the first time the equivalent of this path integral here. So trying to do things as people do in quantum field theory with a sum over histories, except that the history now is about a history of geometries, okay? And so I started at the beginning saying we have to make sense of this expression. We started to understand better this expression in the context of loop quantum gravity here in the end of the 90s. And then we have to wait many years, some 10 years, to finally have an expression that made sense. And this is what we will discuss in these lectures. So the modern version of covariant loop quantum gravity. So in these 10 years between the paper by Michael and Carlo, there was a lot of work. There was in particular a model that was called the Barrett-Cray model, that is one step toward what we have today. The model was incomplete, so the final completion, if you want, came with this work. And it's a pleasure, of course, to be explaining this in Florida because, of course, John Engel was one of the persons that contributed to write down this expression. Of course, there were other people working. So basically, the same expressions was also found by Laurent Freidel, Kirill Krasnov, and then there was the so-called Polish school with Kamiński, Kieslowski, and Lewandowski, who wrote also another version. But basically, it was always the same amplitude, the same path integral. Well, not a path integral, because as we will see now, we have discrete geometries, so it will be a sum. But there were all these people converging. So at the beginning, there was a bit of confusion, as always. People were working on different stuff. And then there were theorems, works that were realizing that all these different expressions were, in fact, just different perspectives on the same theory. And this is beautiful when it happens, right? I should say that even today, you can write your path integral of histories of geometries in different ways. So don't be shocked if I will present you something in these lectures and then you open a paper and you find a different formulation. So it's not that we have a lot of models. So there is one theory. But then, of course, you can use different variables depending on the kind of problem that you are addressing. You can find you can massage your equations in different way. And of course, a good physicist is a good masseur, how to say? It's somebody exactly who is able to find the proper formulations for the different problems. Again, just John Barrett come back into this story because together with his group in Nottingham, proved that this expression, with which at the time we were not able to do so many computations, he proved a theorem saying that this expression had in its belly general relativity. So we were not just doing some funny theory, but we were doing quantum GR. And then, of course, one more step was the definition of the cosmological constant, to which the main person that contributes is Mushin Han, with the different combinations of people through the years. So again, a big pleasure to talk about these things here in Florida. Okay, so this is just to get you oriented in the history, and the next thing is, well, so we have this theory that is sufficiently well defined that you can put it on a t-shirt. So you always, when you define a quantum theory, you need 3 ingredients, okay? You need a Hilbert space. You need to know, so this means that you know what are the states of your theory. Then you need to compute physical quantities with these states. So the physical quantities are the observables of your theory. So you need an algebra of observables. And then you need to tell how these observables evolve, how the states evolve. And this is what the dynamics does for you. And as I said before, you can do this with a Hamiltonian constraint, or you can do this with a covariant formulation of the theory, namely giving transition amplitudes, giving probabilities for states to go from a given state to another one. Before going to this matter, the main matter of the story, that is the transition amplitudes, I need to tell you something about the Hilbert space and the observables. As I said, it's a bit of a repetition with respect to what Christina will be doing, because the kinematical part of the theory is the same, whether you're doing canonical or covariant. But I wanted to give you these informations, these facts, in a flavor that matches better the language of the covariant theory. So that's the plan for today and for the next lectures. So we will talk about the quantum geometry. And today, later in the second lecture, I will start to introduce the spin-foam dynamics. Then I will go back tomorrow to the spin-foam dynamics, rephrasing things in a slightly different language. So you will see how things work a bit more precisely, put your hands a bit more into the details. And then, well, I will not be able to do a full computations. I know that some of the people here wanted me to go through all the details of one computations. The problem is that depending on which computations you want to do, you need to pick up one particular formulations of the theories, and then you have to spend time on this particular formulation, so I'm not gonna do this. But the message I want to convey is that even with just a few informations about these transition amplitudes, even with just a few things, a few properties that you can extract from these transition amplitudes, you can already do physics. You can already say very revolutionary things about physics of cosmology and black holes and so on. So this is what I will try to arrive to tell you in my 4th hour. And then I will leave time, hopefully, for some discussion. And then I will devote the last hour to tell you about my favorite thing, because in the end, I am not somebody who I'm not a mathematician who constructs the theory. I am more of a practitioner. I am someone who used this theory to do physics, and in particular, use this theory to do cosmology. So I will show you how you can use the transition amplitudes to do cosmology. And another thing that I could have done was to use this transition amplitude to do black hole physics, but there are already there are already lectures by Carlo that will be about that. So just wait for Carlo in the end of the week. Good. So here we are. We start our lecture, unless you have a very urgent question at this point, historical question or anything. Yes?
No, it's just a silly question. So why do people have the different name, canonical and covariant? Why do people name it as a covariant theory? Does the canonical is not considered as covariant theory?
Well, canonical because you have to do your canonical analysis of general relativity, define your canonical variables, and this comes with an Hamiltonian, so it's the usual framework that you should know from dynamical systems. And the goal of the quantization is, if you want to put a hat over your H. So you have an Hamiltonian and you want to put the H over the Hamiltonian, and so somehow you quantize a la Dirac in a straightforward manner. So why covariant, the other one? Well, in a sense, because it's it's a formulation in which you preserve more the covariance of the theory. So the fact that you don't, so as Christina was saying before, you have to do things like picking up a particular choice of a foliation in your theory, so somehow you are breaking the covariance. Nothing bad with that. So, I mean, the world in which we live, in which we compute things, when we do a measurement, we have to break this covariance. But so the covariant formulation is one in which you bring this covariance farther with you, let's say. And so the covariance is more manifest. Your symmetries are more manifest, and this is true all the time also when you do quantum field theory. Good. Yeah, but these are just names. In fact, the covariant formulation of loop quantum gravity has also its own name that is called spin form. So the spin form, it's a name that was originally, I think, pushed forward by Wheeler. Is it correct? Yeah, probably. The first person to talk about a foamy space-time. We will see why this name describes well what we have, like bubbles of space-time. Good. So let's start. And we say that the first thing that we have to discuss is the quantum geometry. Yeah, let me go from the basics. In what you have seen in the previous lecture by Christina is the fact that you can define tetrads. In a certain sense, because this is what you would do if you are a good relativist, if you know differential geometry, and so you can arrive to define these things. I studied general relativity, unfortunately, with a particle physicist, and I had to study general relativity from the Weinberg book. And in the Weinberg book, you start with the tetrads in a certain sense, because the idea is that general relativity is a theory in which you promote your reference frames to a field. You have a reference fields. And these reference fields are the tetrads, okay? So, and as I said before, as Christina said before, in the ADM formalism, you pick up a foliation. So this is equivalent to say, okay, I want to study the geometry at a given time. So how do you know which geometry there is? Well, you have to make a measurement. You make your measurement at a given time. So at that time, you define a surface that is space-like, and the normal to this surface that will be your, well, in the IDM formalism is called the lapse. So this constrains the tetrads to triads. And also you have seen in the previous lecture that instead of the triads, you wanted to use densitized triads that are in fact just conjugate variables to the Ashtekar connection. So the connections, as usual in field theory, is where you have the physical content of your field, or you can go, the triads as well can be seen as representing the gravitational fields. There is an equivalence to the metric formulation of GR. And notice the fact that when you define the tetrads, so what you have is that you define your line element in GR, your ds. In fact, you define a ds square that is equal to the matrix times the coordinates. And because it doesn't make sense to associate dimensions to the coordinates, so what you have is that your ds square, that is an area, is equal to the metric that is also with the units of an area. So in a sense, the area in general relativity plays a special role. So you may want to start your formulations of your the formulation of your theory taking units in terms of the fundamental area. So in what I will do later, I will just take 8 pi gamma hg equal to 1, where 8 pi, you know, gamma is the Berberi-Mirzi parameter that you just met, and hg is the Planck area. I take this as my units, equal to 1, and notice the fact that, as Christina was saying before, oops, no, I wanted this, and here you see things turning, and these things have been turning because, of course, for each triads, you have the freedom to orient your triads as you like. That means that you have an invariance, a symmetry, and the rotations. So rotations are described by SO3, but it's convenient, as usual, as we do all the time also in quantum mechanics, to take rather than SO3 as your fundamental symmetry group, you prefer to take the double covering of SO3, that is SO2. So we have these objects, the triads, that knows they are characterized by having this symmetry, that is SO2. Keep this in mind because this is how we construct the theory. Because what I want to do here is to try to construct the theory from bottom up. I want to do it as we do it in quantum field theory 101, or when you study, for instance, Yang-Mills theory, and you're given the symmetries, and from the symmetries you have your variables, and you construct your action, and blah, 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 and so on. So what I want to do to construct my theory here is to say, okay, what are the symmetries? Oh, my symmetries, okay, in general relativity, in fact, we have two different strange symmetries. One we know are the symmetries of space-time, that is the Lorentz group, in fact. And we have another symmetry. The two symmetries are slightly different. We have another symmetry that is the invariance under diffeomorphism. That means that we don't want our theory to rely on a given choice of coordinates. So I wanted to write down a theory without coordinates. That is not what we do in quantum field theory, right? Because you define your fields in a point, you define some function of x. Here, instead, we need to find a solution for this. So we need to say where things are localized without making reference to coordinates. So how do we do? Well, the strategy is to do the same thing that people do when they have a discretized theory. So for instance, well, that's why we were talking also about Regge calculus before. So I want to take a skeleton, some bones, so that I can say where things are. So suppose I take a quanta, a piece and something of my gravitational field. That means I take a region of my space-time. And then I need to say where it is. That means which other regions are in interaction with my region, okay? That means that, okay, I can associate, for instance, one point to my region, and then another point to another region, and then I can say, okay, if they are in interaction, that means that they are adjacent to one another, then I can connect them with a link, okay? So I get this structure that is a graph, that is an abstract graph in which I have nodes and links. And this is just a tool that we use in order to talk about localization in absence of coordinates. So you see, I am constructing the theory from the bottom in a way in which I don't have to talk about coordinates. So in a certain sense, diff invariance, it's written in the belly of the theory. Diff invariance here appears by construction, okay? So I have a graph. This is the graph you see there in this picture, links and nodes. So I can just call this graph gamma, gamma, the Greek letter for G of graph. And in order to define this graph at this stage, just need to tell you how many links there are, how many nodes there are, okay? That's the starting point. And then, so I want my gravitational field to live on this graph. So my states of the theory should belong to this graph. So I can write something that is called a graph Hilbert space. That is what we have written here. So this is my graph Hilbert space. And this graph Hilbert space have a very nice property because it's defined as the direct sum over graphs. And it has a very nice property that is the fact that suppose I have this graph, and then I cancel some part of the graph. So like I do something like this, okay? I cancel, I will tell you how to cancel some links and some nodes. So that means, like, I don't know, the value of my gravitational field in those links is 0. Okay, so, okay, I just cancel it. I have no space-time there, so I have just flat space-time there. So, well, the point is that I can remove part of the graph. I can remove from my description some regions of space-time for any reason. But then the resulting Hilbert space, the resulting graph is a subgraph of my original one. And this implies also, now it's just a mathematical fact, that the corresponding Hilbert space of the subgraph, it's a subspace of the bigger Hilbert space of the larger graph, okay? So suppose you can take a description of your theory in which, in principle, you can take a graph that is infinitely complicated. Then all the possible subgraphs are also included in this description. So usually we do the opposite. So usually we start with a very simple graph, and then we can add complexity to this graph. That means that we refine the graph to make it more and more complex, to include more and more information about localization in my space-time. And in this way, I describe the whole theory. So this is connected to what I was saying before regarding regecalculus, in the sense that I told you regecalculus is classical general relativity, in which we truncate the degrees of freedom of my field theory to a finite number of degrees of freedom. So what the graph is doing here for us is we are not yet quantizing it, even if I am talking about Hilbert spaces, okay? So what the graph is doing for us is just to truncate the degrees of freedom of the theory. So then when I do the quantization, I will have something that is more manageable, okay? But the theory is defining the limit in which I can take a graph that is arbitrarily complex, okay? Obviously, I cannot work with this limit for an infinitely complex graph is not manageable. It's not something you can do on your piece of paper or on your computer. In fact, on your computer, you don't even do that for general relativity. As I said, when people do numerical GR, they take a discretization of GR. So here we are doing basically the same thing. We are just truncating the theory, and we are doing this on a graph. And this completes the discussion of how we insert from the bottom the invariance under diffeomorphism. Now we have the next step, that is that we also want the Lorentz symmetry. This is actually the real gauge symmetry of my theory. So my field, the gravitational field, is a field in which the fundamental variables should be valued somehow in my gauge group, that is the Lorentz group, the one that codes the symmetry of spacetime. So I told you before that we can consider the theory on a given foliation of my spacetime. So remember that the Lorentz group can be decomposed into boost and rotations. And what we were doing before when I was defining the triads, and I was saying the triads have only they have this invariance under rotation. Well, what I was doing, in fact, was just to kill the boost, because as I said, I was making a measurement at a given time, and on my space-like surface, I was just considering the rotation group. So I have SU2. I have variables in SU2. Usually when you do, you consider canonical pairs of variables, you have a position and momentum, and when your variables are valued in a group, usually the conjugate variable is valued in the algebra of the group. So here I have one variable h, that is an element of the group SU2, and I'm introducing here the conjugate variable I call L, that is valued in the algebra of SU2. So now I wanted to use these variables to construct my states. So in particular, I can write these states that you see here. I wrote them here. They are states that are functions of that are functions of my H shell, where I'm putting, I'm considering a group variable for each link here, and here I have the property that that these states needs to be invariant under SU2 transformations. In particular, I implement this gauge transformation, this invariance, for each node here of my graph. That means that for each region of space-time, actually, sorry, let me be precise, for each region of space, because now we are defining things in my choice of slice in 3 dimensions. So I have chunks of space, and these chunks of space needs to satisfy the symmetry of my theory, so they needs to be invariant under SU2. So I implement this symmetry, and this means that my Hilbert space, my graph space, H gamma, is given by square integrable functions as usual. But now, so the square integrable functions, the square integrable functions, we said they have L variables in SU2, one for each link, and I take a quotient because I'm imposing this SU2 symmetry at each node, so n times, okay? So I hope this expression sounds comprehensible. In case you have already seen lattice gauge theory, you will recognize that this is exactly the same Hilbert space that you have in that case. So in that case, you have your gauge symmetry that sits on your lattice, and the shape of the Hilbert space is exactly the same as I have here, okay? So how does it, so I said that that these states are invariant under SU2. And one important consequence of this is the fact that there is a constraint that appears in the theory. So in the space of all possible states that are valued in SU2, I am taking a subspace, a subgroup, that is only the one for which I have gauge invariance. I take, among all the possible states, only those that are gauge invariant. In doing so, so this is equivalent to say that I am imposing a constraint. And this constraint is the one that we see written here, that is the fact that my L, that I introduced before, my L needs to sum up to 0. So what does this L means? Well, first of all, remember, I introduced the L, but the L by themselves, they are not gauge invariant objects. In fact, they transform as vectors, so they are not gauge invariants by themselves. So I needed to take another object that is gauge invariant. And it's very easy to construct such an object because I can just take, you see, the product here of L's, and in particular, I take 2 different L operator, one for one link and one for a different link. So what you have to think about here is that you have a graph, you pick up one of the links, and you look at the L operator that is associated with it, and then you take all the possible pairs with all the other L operators associated with the other links, okay? You sum over all of them, and the result should be 0. And as I said, this is equivalent to impose the gauge invariance at each node. And there is a beautiful interpretation of the object that we have just constructed, because these objects with these 2 vectors is what will be in the theory an angle operator. So we have our first geometrical operator in the theory, the angle operator, that is a gauge invariant operator. So as Christina was saying before, this is a proper Dirac observable of our theory. Now, this is where the magic happens. Yeah, question. There is a question there.
So I'm thinking that maybe these new constraints that you have, like if you take the projective limit in the case where you have like infinitely refined graph, could you recover like the constraints that Christina already showed, or they are completely different constraints, like these constraints with?
One of the constraints that Christina showed, that is the Gauss constraint, is going to be exactly this. Yes.
When you take the projective limit?
Yes.
Okay,
yes.
Thanks.
And so what Christina will do is somehow complementary to what I'm doing, in the sense that I am starting from the bottom, and then I will tell you how this abstract structure can be embedded into the continuous manifold of GR. What Christina is going to do is the opposite, starting from GR, discretizing the theory, and then see how inside you can find these objects that I am describing here. And as I said, I think it's very nice when in the theory you can see things from the different perspectives, but then of course the resulting objects are the same. So thank you so much for making this connection. Okay, so now we are arriving at the main point, to the beginning of seeing what is a quantum geometry, because we can use the spin geometry theorem that I mentioned before to associate a notion of geometry to this very abstract construction. So what the spin geometry tells me is that every time that I have these operators, in fact, this is the Penrose metric operator, that is such that you have the sum that gives 0, then you have automatically associated a geometry in the sense that you can associate a quantum polyhedra. So let me unpack this better for you, and let me connect to what we were saying before. So for each node of my spacetime, I have links that are attached, and you can imagine that you have a vector that is associated with each of them. And so what this Gauss constraint is telling you is that if you imagine that this set of vectors represents a polyhedra, and you can do so because there is a theorem by Minkowski, so very old theorem in geometry, that tells you that every time you have a set of vectors that sum up to 0, you have a classical polyhedra that is associated to this. So this polyhedra is constructed so that, so you take all your vectors, you put all the vectors having the same origin, you want the vectors to act on the same point, and then you have a face of your polyhedra that is associated to each, that is, if you want, perpendicular to each of these vectors. And the area of these faces is given simply by the magnitude of these vectors. So what the spin geometry theorem is telling us is that basically, if you think about this polyhedra being immersed, for instance, you take your polyhedra, you put it in water, and what it's saying is that even if I change the pressure all around my polyhedra, the polyhedra doesn't move. So all the forces, all the pressure is equally balanced. So this is actually the way in which Penrose thought originally about this theorem. But the result is that you don't have simply a geometry. You have something that is a quantum geometry, because now your polyhedra are constructed out of quantum operators. And as such, these quantum operators are, gives a fuzzy geometry, not a perfectly defined geometry, as in the classical case. And the point here is that we started with a construction in which we had just a graph, and we had group variables. But the theorem is allowing me to connect this abstract structure with something that knows about geometry, okay? And I can do it from the bottom up. So what I have is this quantum geometry that is defined in terms of group variables that we have seen are given by the holonomy of the connection, of the Hastings-Barber connection, is my H. And I have these L operators that in fact are just, in the quantum theory, are the generators of SU2 transformations, and they are here in the theory, they play the role of the left invariant vector field. So this is like position and momentum. The L represents your derivative operator in the theory, and they are indeed associated with the gravitational field, in the sense that they are just the quantum version of my tetrads. And the full geometry is given by putting together all these variables, all these different quanta of space that lives on nodes, and connect them using these graph structures that tells who is next to whom. So with these ingredients, we can write geometric operators.
Thank you. This is a rather basic question, but I don't understand what the state is. Is the state the polyhedra, or is the state living on a link or a node?
Okay, so for the moment, what I have done is to define just generic states, this psi of H, that are states that take variables in my group. Now I will, the next thing that I want to do is to define a basis. So I will choose a basis in my Hilbert space, and you will see exactly what the states are, okay? So, but first, because in order to choose a state, choose a specific basis, I have to tell you with respect to which physical quantities these states are eigenstates. So let me first define what are the physical quantity that I can consider. So we have seen one that was the, doesn't want to change. Yep. We have seen one that was the angle operator, beautiful. But we can also define other kind of quantities that are all geometrical quantities. So in geometry, the basic stuff that I can consider are, as I said, area. Well, the area is somehow the most natural quantity that I can describe. It comes just by taking, so before I defined the angle operator taking vectors associated to two different links, okay? So if instead I just take the norm of the square root of the norm of these vectors, so I just multiply L on one link by itself, I get the area operator. So you see how if I have a link and I have elements, I have my L, that, as I say, is in the algebra of SU2, and so I can associate with each link a notion of area, okay? So it's beautiful because I was saying before that the links are telling which region is in interaction with another. So we had one node and another node, and I needed to say whether they are adjacent to one another, but being adjacent means being in interaction. So here I have an area, and you can think about this area associated with the link as saying how much these regions are interacting one another. And if you remember what you know from quantum field theory when you were studying, for instance, scattering amplitudes, well, to know how much interaction there was to give a cross-sections that is an area. So, but here it's reverse. In the sense, we are constructing things as you would do in particle physics. We compute cross-sections in a sense, but here my cross-sections doesn't have just the dimension of the area, is what determines what we mean by area, okay? So I have an area, I can construct this operator that, as I said, it's one of the milestones of loop quantum gravity because, so it's one of the main results that was found in the 90s by Rovelli and Smolin. And now these objects, we say they are generators of rotation, so they are generators of SU2. So from your quantum mechanics 101, you know everything about the generators of SU2 because these are exactly what you have when you study the angular momentum. So you have a discrete spectrum, and this is a genuine quantum discreteness of the theory, not to be confused with the truncation that we took before. So the truncation is like putting your field in a box, but your field has quantum levels, quantum energy levels. So your gravitational field has quantum properties that are manifested in this discreteness, the discreteness of the area, and in an analogous way, you can define a volume operator So the volume operator is again written by combining L operators. And here I have written the volume operator in a very simple manner when you have the most simple tetrahedra that is, the most simple polyhedra that is a tetrahedra. But in principle, you can generalize this expression to any possible polyhedra and then take the limit possibly to n links, so n faces. So this is the main, the core of the story, that you have geometrical quantities that have discrete spectrum, and this is the discreteness of loop quantum gravity. The next thing that I need to do is to write my states so that these states may diagonalize these physical quantities, but I have finished my time for now, so this is the first thing that I will do this afternoon.